So if you were to look at the forces subject to any arbitrary small section, you can notice that the internal shear transferred from the left and the load per unit length times that unit length and the jacking force is going to directly transfer to the internal shear of the next adjacent section. So what you can do from that is start from the left and work out the approximate value or solution to the internal shear across the entire member. And what you can notice is that if there's no jacking force present, then the area of this rectangle, or the small change in length times the load per unit length, is going to directly increase the internal shear at that location. And consequently, the slope of the internal shear at that location is going to be the load per unit length subject to that small section. And what you can do is cut the rail into more and more smaller and smaller sections to yield a better and better solution, a more accurate solution. So if you were to add up all those small changes in the shear and do that as you approach an infinite amount of times, that breathes the definition of an integral and derivative, which might look familiar if you've ever taken a calculus class. So now we can take that same arbitrarily small section and look at the internal moments or torque around a certain point. And we can see that the internal moment transferred from the left and the shear and jacking force applied at that small distance is going to directly equal the internal moment of the next adjacent section, if we assume the load per unit length is small in comparison. And what we can do from that is start at this left assumed internal moment and go from section to section, adding up all these small changes in the moment to get the approximate solution for the moment diagram. And what we can see from that is that the shear force, the value of the shear multiplied by that small distance, which is the area of this rectangle, is going to directly change the moment at that section. And consequently, the slope of the internal moment at that location is going to be the value of the shear force, which is negative in this instance. And if we approach infinitely many smaller and smaller section cuts, we can get the exact solution, which you can write with the notation of an integral and derivative. So how in particular do we determine the slope of each section across the entire length of this member? Well, just by inspection, we can see that the moment will bend the section just ever so slightly, stressing and in turn stretching and straining the longitudinal fibers. And just looking at this particular longitudinal fiber, it makes this sector, and the geometry will tell us that the arc length of this fiber will be the product of the radius of curvature and that small angle, which just so happens to be the difference between the slope at this section and the slope at the next section. And kind of in the same process as we were doing before, we can start at the initial slope and go from section to section and add up and resolve the approximate solution for the slope. And just kind of as a gut check here, like it makes intuitive sense that the slope will start positive and gradually incline until you reach where the forces are, and then become negative, and as indicated by a gradual decline. And after just a little bit of algebra manipulating all this, we can come to the conclusion that the product of the moment and the small change in length divided by the rigidity, which is the dependent on the physical properties of the material and cross section, will directly change the slope, and consequently the slope of this curve will be the exact value of the moment at that location, which makes intuitive sense because the more moment there is, the more bending moment, the more the slope will change. And then, of course, if we were to cut up infinitely many, infinitely small sections, we'd get the exact solution that you can write as the integral and the derivative. So now that we know the slope of every section, we can try to resolve the vertical displacement across the entire member. And we notice that the section at a given slope will vertically displace approximately by the value of this arc length that the section is rotated by. And you might be sensing a theme here, but if we start at our left boundary deflection, we can go from section to section and add up all these small changes in deflection to get the approximate solution. And we notice that the slope multiplied by the small change in length, or the area of this rectangle, will directly increase or jump the deflection at that point. And if we zoom in on just that small section, we notice that the slope doesn't change much because that section is so small, it's constant. And therefore, the deflection at that point will be a straight line, enabling this method to work. And of course, consequently, the slope of this displacement curve will, well, quite obviously be the value of the slope at that section. And of course, if we cut our member into infinitely many, infinitely small pieces, we can get the exact solution for the displacement by the integral and the derivative.